How do we monitor the neutron embrittlement? Specimens in the vessel, right? But it's not a fast process. Neutron embrittlement damage is slow over many years. So we can check after 5 years, 10 years, 20 years, 30 years, okay? And monitor. What do the operators do to make sure we don't have a brittle fracture? What do the operators do? The core designer gives us a low flux core. That's not the operator, that's the core designer. The operator doesn't control the flux. What does the operator do to make sure the reactor doesn't have brittle fracture? He follows the pressure temperature curves that the engineers give him, right? That says what? If the temperature's low, what's our pressure? If the reactor coolant pressure temperature is low, what should we do with the pressure? Keep the pressure low, right? We can't raise the pressure till the temperature gets hot, and we move away from the nil ductility, right? So the operators make sure we never have high pressure in the reactor with low temperatures. So what's the main challenge for feed water heater tubing? The other class couldn't get this one. Yeah, this class looks smarter than the other class. Fretting, what's fretting, right? That's like vibration. It's like hitting it with a hammer many, many times. And what does the tube do? Does it crack? No, the stainless steel tubes don't crack. That's why we like stainless steel tubes, but they thin out, right? And eventually they're so thin, what, they break because the pressure's too much. And what material do we use? I think we just said stainless steel, right? Type 304 stainless. You read that in the tubing paper. And what do we use for piping and components in the turbine cycle? Carbon steel, right? 0.2% though, right? And what's the main challenge? For carbon steel in the turbine cycle? FAC, right? And what influences FAC? What's the number one thing that makes a difference in the FAC? The amount of chrome, right? If I just put in a little bit of chrome, I go down 10 times, right? So what are the other things that influence FAC? Temperature. How much FAC do I have if the flow velocity is 0? None, right? You need flow velocity. So flow velocity and pH and oxygen, right? How much oxygen is good? No oxygen? You need a little bit. If you take all the oxygen away, FAC is really bad. You need a little bit. Too much oxygen, you have general corrosion attack. Too little oxygen, you have too much FAC. You need a little bit of oxygen, right? And how do we monitor FAC? We identify where the FAC occurs, put a grid system under the insulation, and come back and keep measuring it. Every week? How often do we measure?
Every day.
Every day.
And we notice, we walk in the plant every day.
You can't see FAC from the outside, right? FAC is from the inside. So how do we see FAC with the grid system? Ultrasonic, right? We ultrasonically measure the FAC. How often? Every month? Every 6 months? Depends, right? If it's a high FAC, we might come back every year. Most FAC, we can come back every 2 years, every 4 years. But the thing about FAC is it's very uniform, a very constant rate. So there shouldn't be a surprise. So as the pipe gets thinner and thinner, we can make a prediction. Oh, the pipe will get too thin after 6 years, so I have to make a plan today to replace the pipe. Who says the pipe is too thin? How do I know if the pipe is thin enough or thick enough? How do I know? What do we call that? What do we call the amount of thickness we need? Minimum wall, the minimum pipe wall, right? So if the pipe wall is a little bit bigger than I need, but after 1 year it becomes below the thickness, I got to do something. So what are the things to do? If the pipe wall is becoming too thin, or the feed water heater shell is too thin, what are the options? What can I do? I can remedy it. How do I remedy it? Weld overlay, right? So if it's a limited area, I can just keep welding till I add more metal, right? What else can I do? If it's a bigger area,
Replace this one.
we can replace the whole section like a window, we call it. We cut out a window and weld in a new one, but that's hard because I have to have the right shape and the right curvature. So what else can I do? I can put a cap on top, right? I can put a cap. And then what's the worst thing I have to do? Replace. Throw it away and replace it, right? But in this room, we shouldn't have that because we aren't going to have FAC, right? That's the old plants. That's the old headache. Do you want to give this headache to your kids when they operate your plant? I don't think so. How do we avoid FAC? I think we all know that one. So what are the two kinds of materials? What are the two categories for piping material? Metallic and non-metallic, right? And what's the advantages of non-metallic? Number one advantage. Sometimes it's not as cheap as you might think. Depends on the service. If it's very low pressure and low temperature, it's very cheap. If it's higher pressure and higher temperatures, then it can become more expensive than steel pipe. So generally cheap, but that's not the main advantage. Corrosion resistance, right? Seawater, fresh water, raw water. Okay? And what's the disadvantage? Pressure and temperature ratings are very low, okay? Not the kind of pressure and temperature ratings we need. Anything else is a disadvantage? It's not very stiff. So if we route it above the ground, we need a lot of supports, right? But that says, where's a good place to put the pipe? Underground, right? So if we're moving water around, we move it underground. In fact, at the nuclear plant, many times they will put the plastic pipe in the ground, but when you come to the power plant, they switch over to a metal pipe that's exposed. For one thing, the code for safety-related piping will only let you use plastic if it's buried. They won't let you use plastic if it's hanging on hangers in the building, so far, till now, okay? So a very good application is buried pipe for raw water, seawater, anything that corrodes. The life of this piping is forever, 100 years maybe. What's the best material we have for that kind of piping? What's the name? Anybody know? HDPE. What is that? Anybody know? High density. I spelled it wrong. High density HDPE. High density polyethylene. Okay. It's a kind of a plastic. And what's the main advantages of metallic piping? It's strong at temperature, right? It has high pressure and temperature ratings, up to 600 centigrade, right? Can I use carbon steel at 600 centigrade? Yeah, everybody says yeah?
No.
No. No. We use P11, P22, but especially nowadays P91, P92 at those very high temperatures. But for our temperature in the nuclear plant, 300 centigrade, carbon steel is just good, just really good. Okay? And what's the disadvantages of metallic piping? Mostly corrosion and cracking, right? Those kind of things. What is the minimum wall? Minimum wall is how thick the pipe has to be based on what? Code. And we use a capital letter for code. What does that mean? What is the code? The piping code, right? Power piping code. So for non-safety, we use B31.1, power piping code, right? And then for safety related, we use ASME, boiler and pressure vessel code, what section? Section 3, right? Okay. And then there's different subparts of that, okay? We might call class 1, class 2, class 3. They have a little bit different rules. But these tell you how thick the pipe has to be, okay? What's a corrosion allowance? Who says the corrosion allowance? Do I look inside the code to find out the amount for the corrosion allowance? Just go to the code and find out, right? No. The owner, the designer, the engineer decides how much corrosion allowance, right? Now nowadays, if we pick the right material, we shouldn't have corrosion. Our corrosion allowance can be very small, okay? But in the old days, they used to put a big corrosion allowance. They say, oh, after 30 years my pipe will get thinner and thinner. That's a bad design choice nowadays. We know all the reasons that a pipe can get thin. We don't want the pipe to get thin. We don't want to buy extra thick pipe and just watch it get thinner. We can pick the right material so we don't get thin pipes. Pick the right material and pick a small corrosion allowance. What other things do we check for the pipe stress? Longitudinal stress, right? So when we calculate minimum wall, that's hoop stress. That's the radial stress this way. But the pipe also goes this way. So what causes stress when you're stretching the pipe like this? Pressure, right? So one thing is the pressure pushes out this way. So think about a balloon. You blow up a balloon, it gets out this way, right? The pressure pushes it this way. We have stress in that direction. But the balloon also gets long this way. We have stress in that direction. So pressure stretches it like this. We call longitudinal pressure stress. What else makes stress long way? Bending. Where do we worry about bending stress? On the inside of the curve or the outside of the curve? Outside. Why? It's tension. It wants to make cracks open up, right? What's the inside of the curve? Compressive stress, right? We don't worry about that. We won't have cracking, right? So the outside has tensile stress, makes cracks. We measure the stress there with our analysis and make sure it's below the code allowable. What else could make bending stress in the pipe, make the pipe bend? What's that? How about earthquake? Earthquake shakes the whole building, right? Now the pipe is shaking and bending, right? So we could have seismic stress. What else could make the pipe dynamically respond? Yeah, fluid transient, right? Water hammer, right? If we have high-speed water and close a valve, what happens? It's like a car hits the wall. The water stops. It makes the whole pipe shake, okay? Where do you think the water hammer is a problem? In little pipes, with little valves, with little thin wall, or with big pipes, with big flow, with thick wall? Which one has a bigger water hammer problem?
The second.
The big pipes. Because there's so much water flowing, right? So little pipes and water hammer are usually not a problem. What do we mean by standard pipe? How do I pick the size of my pipe? Do I want a small pipe or a big pipe? How do I decide? How much flow is going through there, right? So I have a standard flow velocity. If it's oil, if it's water, if it's steam, if it's air, I have a different velocity for each one, right? So I calculate the amount of flow, and I look at the area and say what velocity I want. And that says the size of the pipe, the diameter. Now I know the diameter, right? So I just call up Posco Steel and say I want 27.113 millimeter pipe?
No.
No. Why not? They won't sell that to me?
No.
Oh. I have to buy a standard pipe, right? So I look at the size and I pick the next bigger or next smaller size based on my velocity, how close I am on my velocity, right? And then once I have the size on diameter, then I look at the pressure, right? So the diameter is fixed on velocity, but then I look at the pressure and figure out the thickness, and each size has different thicknesses. And what do we call the different thicknesses? What's the name for that? Schedule. Schedule 5, Schedule 10, Schedule 40, Schedule 80. Standard schedules, okay? And why do pipes fail? I don't know, is people from different classes? Because we didn't do one of the classes yet on piping. So I don't know how many people did the piping class or not. Why do pipes fail? We know one reason pipes fail. Surrey and Mihama, why did the pipe fail? Fail means break. Why did the pipe break? Fact. Okay? But the number one reason pipes fail, did anybody take the class?
Vibration.
Vibration, right? And why do we have pipes vibrate? What can cause a pipe to vibrate? Rotating equipment, like a pump. Reciprocating equipment, like a pump or a compressor, right? That's a big cause. But we also have flow-induced vibration. Okay? So there was a power plant in Illinois that had lots of problems because the flow was going past, so the steam flow was going through here, and it was going past this dead end. This was closed. The valve was closing it here. But it would come in here, and then we would have vortex shedding, okay? And that caused so much vibration that it broke the reactor vessel internals. And they went inside the pipe and moved 100 meters down the pipe. Big pieces of steel from vortex shedding. So that's fluid-induced vibration. How do we avoid FAC? We all know that. Get some chrome in the carbon steel, right? How do we avoid vibration failures?
Support.
Yeah. So the designer has a very hard time predicting where will be the vibration. How much is the vibration? We don't have analysis tools. The piping guy has analysis tools to look at the stress from the pressure and the bending and the thermal and the seismic, but they don't have tools to predict where will be the shaking from the vibration. So what do? Startup testing. Very careful before we start the nuclear reaction. We start all the water flowing around the plant, and we look at 0 flow and 10% flow and 50% flow and 100% flow. We look at all the power levels and all the temperatures at all the places we might have vibration. And if we have vibration, what do? Well, the first thing we can do is we can do analysis and say, I measured so much vibration. Is that a problem? Now, if you study fatigue and fatigue life, you know if I have big vibration, I will make a crack, and the crack will get bigger and bigger and fail. But if I have small vibration, I can do that forever. I can do that for 100 years and never have a failure. Okay? So the first thing I can do is analyze the amount of vibration and say, is that a problem? If it's not a problem, it's okay. I'll just keep monitoring. But if it's a problem, what do? I can add some supports or move. Sometimes we just have to move the support one way or the other, and that will reduce the vibration. Okay? What is this? It's a part of a pressure vessel that was what? Cut out to make a window. And here's the replacement window, right? And what do you call this appearance on here, this plate? Anybody remember? It's due to FAC, but what do we call that kind of FAC result? Tiger striping. So it looks like the stripes on a tiger. You might not think that looks like the stripes on the tiger, but that's the name, okay? Tiger striping. What's this? Tube bundle plugging map. So the blue color shows where the tube is plugged and not having water inside anymore, right? So we use this to figure out where is the fretting. Red has a lot of fretting, right? Green, not so much fretting, okay? And how about this one? We took the cylinder wall of a feed water heater and unwrapped it and showed it like this, and what are we showing? Thickness, right? This is a FAC map of that wall. This is our grid system. It's not for a pipe, it's for the whole heater shell. And we see where the FAC occurred, right? There was no FAC here. Do you know why there's no FAC here? Because they put a stainless steel plate on top of the carbon steel. So this was, the shell came down and then had an angle like this, and they thought, oh, the steam will hit that shell. We better put a protection plate there. So they put a protection stainless steel plate, but what happened right at the edge of the plate? Back. And then what happened where the steam went up like this and then hit the head? The spherical head is just past here. They didn't put a stainless steel plate up there, and what did we get? We got the hole in the head, right? So this is a fact map, this is fact, this is tube plugging and fretting. And what is this? Anybody recognize this? I've got flow, turbulence, and flow. This is the oxide layer on the carbon steel. This is the iron. This is iron down here, Fe. And the iron migrates through the oxide layer and gets carried away like this, okay? So this is all water here, and the iron dissolves into the iron and then gets carried away. Even though there's still an oxide layer, it's not a complete layer, okay? So maybe, I don't know the material science of fact, but maybe if we have chrome here, the iron disappears, but the chrome stays, and then the chrome forms a protective layer down here. That's my theory. 0.2 is only 1 out of every 500 iron. But if we remove 500 iron and the chrome is still there, and then it's more chrome and more chrome, eventually we get a chrome layer here that forms protection. Okay? What does this curve show us? What's this way? Temperature. This is FAC rate, right? So FAC has a worst condition. What temperature? 300 Fahrenheit, 150 centigrade, right? So there's a good chance you'll see a curve like this on the test, but it won't have any label on the axis. It'll say, what does this shape show? And you say it's FAC versus temperature, right? And how about this curve? What is this one? High and then down and low. What does this show? FAC rate versus chrome, right? 0 chrome, very high FAC. 0.2 chrome, the FAC became very low, right? So remember that shape, like that, right? And what does this one show? FAC rate again. FAC rate versus pH, right? Looks like the minimum pH is 11.5. So why don't we just pick 11.5 pH? It's very hard to get 11.5. We need to add a lot of additives to the condensate to get that, just too much. We used to control at 9.2 and they moved it up to 9.4, but that's kind of a practical limit. Okay? But anyhow, we're in a good range down here with the pH. So know that shape of that curve. What is this? What do we call this? What is this? Condenser tube bundle, right? And how about this one? Feed water heater, okay? And how about this one? Moisture separator reheater. So the moisture separator part is in the bottom, and then the reheater bundles are on the top. So the steam comes through the moisture separator and immediately goes into the reheater bundles. And now, anybody recognize this one? Pardon? What's on the inside of this tubes? Water. And what's on the outside? Hydrogen. Thin tubes. You never see water on the outside of a bundle like that. So this is a hydrogen cooler. Where do we have a hydrogen cooler? Main generator, right? Main electrical generator. So I'll tell you, this one is chlorides this way. Logarithmic, 0.01 to 10,000. And this way is oxygen, 0.01 to 1,000 parts per million. What does this show us? Stress corrosion cracking. Where is stress corrosion cracking a problem? Do we have a problem with high chlorides and high oxygen? Low chlorides and high oxygen? High and high, low oxygen, or low and low? Where do we have a problem with stress corrosion cracking? Yeah? So high chlorides is here, and is it high oxygen or low oxygen?
Low.
High. Stress corrosion cracking is over here, right? So how do we get rid of stress corrosion cracking? Come all the way down to this corner, right? Low chloride, low oxygen. How do we get low chloride? Now where are we talking about stress corrosion cracking here? Austenitic stainless steel in high temperature water. Where do we have that? Where do we have high temperature water interfacing with stainless steel? Reactor coolant system, right? Stress corrosion cracking. We talked about reactor coolant system, right? FAC is not in reactor coolant system. It's in carbon steel systems. This is in stainless steel, right? So how do we get low chlorides in the reactor coolant system? We keep them out and take them out, right? So we never let chlorides in. So any water we let in has to have very low chlorides. And after that, what do? If any chlorides show up, get them out of there. How do you get them out? How do you get chlorides out of the reactor coolant system? CBCS, right? So we take a very small flow, 100 gallons a minute. What's the first thing we do?